let's talk about something huge. I mean, literally, world-building huge. Forget your high school chemistry class, because today we're not just learning, we're unlocking the master toolkit that's being used to build our entire modern world. We're going to see how we learn to command matter at its most basic level, arranging atoms one by one to literally forge the future.
Think about this. For pretty much all of human history, we've named our great eras by the materials we could just find lying around. The Stone Age, the Bronze Age, the Iron Age. We were basically scavengers, limited by what the planet happened to give us. Well, that time is over. For good. We are now living in a profoundly new era, the age of atomic design. This isn't about finding things anymore. It's about making them. And this new power, it poses an entirely new and much deeper question for all of us.
So let's open up our atomic toolkit. Here's the game plan. We're going to start with the blueprint, the atoms themselves. Then we'll look at the universal glue that sticks them together. After that, we'll dive into architecture, the battle between order and chaos. Then we'll uncover the surprisingly powerful role of imperfection. And finally, we'll look at the incredible things we can now build. Ready? Let's get into it.
Okay, first up, the age of atomic design. This is all about a massive shift in how we think about the world, a shift from simply finding materials to actively forging them.
And this really gets to the heart of it, doesn't it? The challenge of our time isn't about capability anymore. It's about purpose. Just look at the phone in your pocket. That thing has over 60 different elements inside it, every single one chosen and placed there with incredible precision. So we know we can do it. The power we have is, well, it's kind of staggering. The real question, the one that's going to define our generation, is a creative and a moral one. With all this power, what should we be building?
All right, let's grab our next tool, the atomic blueprint. You can't build anything without an ingredients list, right? Well, figuring out our cosmic list of ingredients was this epic detective story that literally took thousands of years to solve.
The case file opens way back with the ancient Greeks. You had Plato, who thought everything was made of just four things: earth, air, fire, and water. Simple enough. But then there was this other guy, Democritus, who had a wilder idea. He said everything was made of tiny, indivisible particles he called atomos. Plato was apparently so infuriated by this competing theory that he wanted all of Democritus's books burned. I mean, talk about the ultimate block button, right? Well, it took just about 2,000 years for science to catch up. John Dalton brought the atom back, saying each element was its own unique type of atom. But the real masterstroke came from Dmitri Mendeleev. He didn't just make a list, he created a map so powerful it could see into the future.
And this is where it gets just mind-blowing. This is Mendeleev's genius on full display. He was so confident in his periodic table that he left empty spots for elements that no one had even discovered yet. And he didn't just leave a blank space. He predicted their properties with stunning accuracy. He called the element that should be under silicon silicon. He predicted its weight, its density, even the kind of oxide it would form. Years later, an element named germanium was discovered, and it was an almost perfect match. This was the moment we realized this wasn't just a list. It was a predictive map to the universe's fundamental building blocks.
So we've got our ingredients. Awesome. But how do you get them to stick together? That brings us to our third tool, the universal glue that binds atoms. And to understand it, we're going to start with a little mystery from the animal kingdom.
I mean, seriously, look at this gecko. How in the world does it just casually walk up a perfectly smooth pane of glass? It's not using little suction cups, it's not sticky, so what's the trick? The secret, it turns out, is to harness the absolute weakest force in our entire toolkit, but to do it on an unbelievable scale.
The secret is a spooky little something called the van der Waals force. Now, even in a perfectly neutral atom, its electrons are constantly whizzing around. This random motion creates tiny, flickering electrical imbalances, little hot spots of positive and negative charge that can weakly attract other atoms. A single one of these attractions is, well, it's next to nothing. But a gecko's foot is covered in millions of tiny hairs, which then branch out into billions of even tinier tips. This creates an enormous surface area, letting billions of these incredibly weak forces all pull at once, forming a bond strong enough to hold the gecko's entire weight.
It's a masterclass in atomic engineering, courtesy of Mother Nature.
Okay, so beyond those weak forces, you've got the two heavy hitters, the main ways atoms form strong bonds. And you can just think of it like this: taking versus sharing. In an ionic bond, like what you find in table salt, one atom, sodium, straight up gives an electron to another atom, chlorine. Now one's positive, one's negative, and boom, they stick together like tiny magnets. Then you have covalent bonds. This is the sharing is caring model. Here atoms, like the oxygen and two hydrogens in a water molecule, actually share their electrons to feel complete. And these two simple ideas, taking and sharing, are pretty much how all the strong, stable matter in our world is built.
Okay, so we've got our atoms and we've got the glue. But a material's properties also depend on its architecture. Our next tool is all about understanding this arrangement in 3D space and the critical difference between order and chaos. At the most fundamental level, solid materials come in two main flavors. On one hand, you've got crystals. In a crystal, the atoms are arranged in a perfectly repeating, totally predictable pattern that goes on and on. Think of neatly stacking cannonballs into a pyramid. It's orderly, it's efficient. Then, on the other hand, you have glass. In glass, the atoms are what we call amorphous. They're just frozen in a jumbled, disordered, totally random state, like a tangled mess of spaghetti. Same atoms, same bonds, but a completely different architecture. And that architecture is everything, as we can see in one of the strangest objects in all of science.
This is called a Prince Rupert's drop. You make it by dripping molten glass into a bucket of cold water. The outside surface cools and solidifies almost instantly, while the inside is still a hot liquid. As that molten interior finally cools, it tries to shrink, but it can't. It's trapped inside that rigid outer shell. This pulls the surface inward, creating enormous compressive stress on the outside and incredible tension on the inside. The result? The bulbous head is so strong you can hit it with a hammer. But that fragile tail holds all that stored-up energy in check. You give that tail the tiniest little snip, and all that internal strain is released in a violent, explosive shatter. It's a perfect and kind of scary illustration of how engineered chaos can create both incredible strength and a hidden, catastrophic weakness.
So far, we've focused on perfect blueprints and ideal, orderly structures. But our next tool is the most counterintuitive one in the box, and maybe the most powerful. It's the secret weapon of every atomic designer, the power of imperfection. Here's a puzzle for you. If you sit down and calculate the theoretical strength of a perfect metal crystal based on its atomic bonds, you get a certain number. But when you go into a lab and test a real piece of metal, you find that it starts to bend and deform at a stress that's about 100 times lower. It's 100 times weaker than it should be. So, what gives? Is this just some fundamental flaw in how things are made, or is it actually a feature?
The answer is a defect, a flaw in the crystal called a dislocation. Think of it like this. Imagine you need to move a huge, heavy rug across the floor. Trying to drag the whole thing at once is incredibly hard. But what if you make a little ripple or a wrinkle in the rug at one end, and then just easily push that ripple all the way across? Much, much easier. Well, that ripple is the dislocation. When you bend a piece of metal, you're not breaking all the atomic bonds at once. You're just easily sliding these little ripples through the crystal. So the crucial point here is that this weakness is exactly what makes metals so incredibly useful. It's what makes them malleable and ductile, why you can bend them and shape them instead of them just shattering like a piece of pottery. The imperfection is the strength.
And of course, nature is the undisputed master of using imperfection. Just look at spider silk. At its heart, it's a polymer, which is just a fancy name for a really long, tangled chain of repeating molecules. But the structure of that silk isn't perfectly ordered, and it isn't perfectly chaotic. It's a complex, brilliantly engineered mix of both. It has tiny crystalline regions that provide incredible strength, and those are embedded within a messy, amorphous matrix that provides flexibility and stretchiness. This combination of order and disorder, of perfection and imperfection, is what creates a material that is, pound for pound, 5 times stronger than steel.
Okay, we've assembled our toolkit, we have the atomic blueprint, we have the universal glue, we have an understanding of architecture and the power of imperfection. We are officially atomic designers. So, for our final section, let's look at the frontier. What will we build?
With these tools, we can start to tackle some of humanity's biggest challenges. We need clean water. We can design advanced membranes atom by atom to desalinate the oceans. We need better batteries for a clean energy future. We can engineer new crystal structures for more efficient energy storage. We need to build more sustainably. We can literally use focused sunlight to sinter sand into glass, with no fossil fuels required. We can even create smart materials, like self-healing polymers that can sense damage and repair themselves, just like living tissue.
We started by saying that the question is no longer, can we make it, but what should we make? We now have the power to design and build the material world from the ground up. The toolkit is in our hands. The blueprints are ours to draw. So the question is now yours. With this power, what solutions will you design? What problems will you solve? What will you build?